Welcome everyone to this lunch talk. Hope that you've been having a good day so far, and you're gonna enjoy this talk as you're having your lunch today. Now, what I'm going to talk about today is recommended systems. But first of all, just to get you a bit of a sense of myself. So I'm currently a faculty member at the School of Computing Information System at SMU. So recommended systems is my research area. So I've been doing this for a number of years now. But at SMU, we also teach courses, and I teach courses at a few different levels, including undergraduate in data structures. The recommended systems is also a course that we deliver as part of the Master of IT in Business. And I'm also teaching machine learning at the PhD level. So now as we go ahead and do the talk, and you have questions, feel free to put in your questions in the Q&A anytime. And once in a while, I might just look at whether there are questions there and get to your questions right away. All right, so here I think on the bottom left corner, you might also see Prepare.ai. In case you're wondering what that is, that's essentially a research group. This is a research group at the School of Computing Information Systems. We are focusing on AI and machine learning, particularly with respect to preferences and recommendation. So there are going to be some examples that I bring up that is also part of the work of the group as well. Now, let's get right to the heart of the problem, which is that of recommended systems. Now, the origin of recommended systems essentially is the problem that we face online with regards to choice explosion. Now, if we go back even a few decades ago, and let's say we are looking for shoes, now what most of us will do probably is going to go to some department store, or maybe some shoe shops and so on, and we're going to choose among the shoes that they have over at the shop. Now, in any one shop, they probably can't stock that many shoes. So in that case, then you're going to have to choose among the options that you have just within the inventory of the shop itself. And usually there aren't that many. Maybe you go through 10s or 20s kind of different options and choose what you actually want. But today, if you go online, as most of us do now, let's say you go to Amazon.com, and let's say if I were looking for men's shoes, then I would type in men's shoes, for example, and Amazon might show me 133,000 results. Now, I probably wouldn't have the time to look at every single pair of shoes on offer. So that's not something that's practical to me. And I might say, hey, this is way too many options. I can't cope with this. Let me just try another store. Now, let's say if I go, okay, can I look at Lazada? And this is Lazada in Malaysia. Okay, so and they even have more options. Now we are talking about 613,000 possible pairs of shoes. If you go to Tokopedia, which is an Indonesian online store, there are now 1.7 million results for men's shoes. If you go to Taobao, now there are 4 million results. Now you can go and say, okay, that's because the query is too general. Maybe I should put in a bit more details, like what kind of shoes you want, and so on. But no matter what kind of queries you put in, there are still going to be way too many options for you to consider one by one. And this is a phenomenon that is relatively new in the sense that in just like maybe in the past decade or two, where the proliferation of e-commerce means that there isn't a limit to inventory anymore. Any shop can stock any number of things because we can just order them online, and then at some level it's going to get delivered to you. Now, so the solution to the choice explosion essentially is recommended systems. What it simply means is that basically there isn't a single shop for all of us. There is going to be one shop for each of us. Now, in this case, Amazon, in response to your query, or any other online store, in response to your query, they're going to give you an interface that is different from what any other user is going to get, meaning that there is essentially a personalized store for each of us. And the reason why that is necessary is because we need to navigate these systems in order for us to be able to identify what we need. And if we can't find what we want, we are not going to make a purchase, and then the shop's not going to make a profit, and so therefore by necessity we have to solve this problem. Now, in psychology, there is something called the embarrassment of riches, the paradox of choice, where we can't make a choice if there are too many options. So therefore, the job of recommender systems essentially is to narrow it down to just a few possible options that you're most likely to prefer. Now, in the past, this is probably a job that is done by, let's say, a human, in the sense that there is the owner of the store, and then as they talk to you, they probably can understand your needs, and then they will recommend, okay, why don't you consider these few options? And that usually helps to some extent. And in a way, the shopkeeper increases his or her chances of making a sale, not by showing you more options, but by showing you fewer options that are better suited to you. And in some sense, what recommended systems today essentially is an algorithm that does that at the individual personalized level. And today what we're going to do is to kind of peel off a couple of layers and just to see what is really ongoing within this kind of systems, and what sort of trends are affecting or are changing the way the recommended systems are being built right now. All right. Now, if you go to Wikipedia, just to find a definition, what is recommended systems? Then it will say, hey, this is a subclass of information filtering system that seeks to predict the rating or preference a user would give to an item. Now, the key word here is that it's an information filtering system, meaning that essentially we're going to filter. We're going to identify a few options that not most people, but the individual is most likely to prefer by trying to predict what their preferences would be. Now, in order for us to predict what these preferences of a user might be, we will need some data. And essentially today's recommended system is a data-driven system. And if you look at all these different systems that you interface on a day-to-day basis today, be they e-commerce, Lazada, Amazon, media like news, YouTube, travel, right? Booking.com, music, Spotify, or different sort of a point of interest like Foursquare and Yelp. All of them will provide some form of recommendation. And the key to the recommendation is understanding you as a user, what you do, and so on. Now, this is a bit of a different paradigm from what we have faced in the past, because in the past, there is only a single or maybe a few TV channels. Then it's up to you, the user, to switch to the channel that you want. That means you are choosing what you are going to get. In a way, I think last time there were many radio stations, and again, Class 95, 93.3, and so on. And again, the burden is on you to choose which channel you're going to listen to. Today, there aren't those kind of channels anymore. In fact, I think if you go to YouTube, probably the kind of YouTube recommendations I'm getting as a person might be different from what you're getting. So in some sense, the burden now is on the part of the service providers to customize an experience that is going to be unique to you. And the only way they can do that is by studying your preferences. And therefore, the basis to a lot of recommendation is basically what we call feedback. There is usually some form of feedback loop where a system might provide you some recommendation, and then you give it some feedback that either enforces or that goes against what their recommendations are. And generally speaking, the two main categories of them are what we call explicit and implicit feedback. In the explicit case, these are the cases where you're going to state your preference very clearly and observably. Now, online, this could mean that you write a review, or you rate a system, or you thumbs up, thumbs down for like a particular Facebook post. Now, these things are very explicit. Thumbs up means you like it. Thumbs down means you don't. It's not ambiguous at all. And generally, these are used to build personalized profile models to predict your preferences. Now, the problem with this explicit data or explicit feedback is that there aren't that much of them. Because if you kind of think about what indicates that you probably like an item, like watching a movie that is recommended, buying a particular product that is recommended, and all these things are pretty clear signals, but they're also costly, meaning that it costs you either time or it costs you money to actually express it so clearly. And therefore, they are also very scarce in the sense that the system probably doesn't have access to a lot of those kind of data. I mean, let's say he's trying to predict what kind of TV you're trying to buy. I mean, how many TVs any one of us is going to buy over our lifetime? I mean, it's not usually a lot. And therefore, this sort of explicit feedback is very, very rare. And therefore, they are not always the most important builder of recommendation. Now, instead, the other side is what we call implicit feedback. These are the kind of feedback that are generally ambiguous, but they are numerous. So in the sense that, let's say you're starting to look for a fridge, you start to go to a particular website, you start to click through things, you're actually providing a lot of signal. So for example, you go to Amazon, you say fridge, and then there are many different fridges that they show you on the first page, and you start to click on some of them. Okay, now there are some implicit ideas behind your clicks. It might be that you're influenced by a particular brand. Maybe you just heard good stuff about a particular brand. Or maybe you are influenced by a certain kind of keywords. The system doesn't know exactly those things, but through your clicks, they can infer these things. Now, it could also be that some of your clicks are actually erroneous click, meaning that it's not that you really meant to do the click. You just your mouse is off by a little bit, and then you accidentally click on something, or that it just so happens that there is an ad, and then you're trying to close it, but you actually end up clicking through it. Now, in some sense, some of these clicks are noisy, but because they are so numerous, there is still some signal behind the noise that can be used to build recommendations. And a lot of the recommendation systems today are actually built on implicit feedback. They are things that we don't realize are actually giving the system a lot of information. Now, for example, think about whether next time you put in a query on a particular system like Amazon or Google or anything else, then they're going to show you 10 links, 10 options. And then you look through things and you're going to see, okay, 1, 2, 3, and then you click on the link number 4. Now, implicitly, you're giving the system two types of feedback. One is that you think the number 4 could be relevant, but at the same time, you're also implying to the system that number 1, 2, 3, those that you skip, might be some things that you don't like or you don't prefer. So therefore, there is a lot of things that the system can implicitly learn from your behavior in order to build the recommendations. Now, a lot of these data-driven approaches have been popularized in the past 20 years or so. And it started out, originally, people thought recommendation systems is a marketing problem. It's a marketing problem in the sense that let's talk to the marketing departments and ask about how they understand about human psychology, how do we market different things, and therefore the idea is that the burden is on these product designers, manufacturers to design things that people want to buy. Now, it turns out that there are certain classes of products where there are a lot of other things that come into the picture because they are cultural influences. There are some of those examples actually are movies. So Netflix were some of the early companies that started to run into this problem because they realized that everybody wanted to watch the popular movies. So Netflix used to be a DVD rental company. So when you say you want to watch a movie, they will mail you the DVDs, and then you receive it over the mail. Now, there is a limit to the number of DVDs that you're going to have, and they don't want to overstock on just the popular movies because the popular movies are trendy. After a few months, nobody wants to watch those things anymore, and therefore then the DVDs, the cost of producing the DVDs are essentially lost. So now Netflix needs a new system in order to surface other movies that may not be currently popular or may have been older movies, but people might actually still like to watch. And therefore now they need to understand how people express their preferences and how they can get recommended different movies. And that helps Netflix to balance out the demand with respect to the different movie inventories that they can loan out to the users. So they created a contest, and the contest was run in 2006, so that was 17 years ago, and they promised $1 million to any solution they can beat their own solution by 10%. It means that Netflix already has an internal solution, and they just wanted an improvement by 10%. And if you can do that, then they're going to give you $1 million. And it turns out that after the contest ran out in the first phase, there is no single team that could beat the 10%. So the problem was essentially difficult enough, and we're going to get to some reason as to why this is a difficult problem. But then they start to allow in the second phase consortia to appear, meaning that the teams can start collaborating with one another. And eventually, the team that came up on top is something called Belcour's Pragmatic Chaos. That was actually made up of multiple teams. Belcour is a team, Pragmatic is another team, Chaos is another team, and they get the $1 million prize. And one of the things that came out of the Netflix experiment was that, hey, it turns out that this is a data-driven problem. And not just that, there was emerging a particular paradigm of solving the problem that turns out to be pretty important. And this is called matrix factorization. And this is this paragraph came out of a report that is written by the winners of this Netflix prize. And okay, a couple of important things here. Firstly, they say that the winning entry consists of more than 100 different predictor sets. Now, why 100 different predictor sets? Well, that's because they were consortium, so the model was built from agglomeration of many different models. But the majority of them are factorization models. Now, let's take a look at what the factorization model is. The basic idea is that okay, this comes back to our high school algebra, like linear algebra, so matrices and so on. But the basic idea is that the users express preferences to the movies, and you can formulate them in terms of a matrix, the matrix of ratings. This could be ratings, it could be clicks, and it could be something else. Now, this matrix that a user assigned to movies in terms of the ratings and so on, they are very sparse. Sparse meaning that there are very few entries. Now, but you can feed it into a linear algebra formulation, and you can solve the problem in terms of factorization. Now, we all learn from math, factorization means that there is a big thing, and we try to factorize it into smaller numbers. And then when you multiply the small numbers, you get back the big number. Now, essentially, it's a similar kind of process, except that we are doing it at the level of matrices, meaning that it's rows and columns of numbers. So now the problem comes down to, can we identify a column of numbers for users, a column of numbers for movies, and they become the identifier, the DNA of the user preferences and the movie preferences, such that if I take the user code and I multiply by the movie code, I get a prediction for how likely it is that the user is going to like the movie. Now, there is a formulation that you need to solve, and that's kind of where the machine learning comes in. But just to get you a bit of a simple example, so let's say in this case, we have 7 users, 1, 2, 3, 4, 5, 6, 7, and the 7 users watching 6 movies: Nero, Julius Caesar, Cleopatra, Sleepless in Seattle, Pretty Woman, Casablanca. So they will make up a matrix that has the shape of 7 by 6. So 7 rows, 6 columns. 7 rows are corresponding to the users, 6 columns corresponding to the items. And then we had some observations where the +1s indicate preferences, the -1 indicates negative, meaning that they didn't like it. Think of it like thumbs up, thumbs down. And let's say the zeros means that we just never observe anything. Now, the problem comes to, can we factorize this matrix that we see on the left into 2 smaller matrices? For every user here, we have a code of 2 numbers. For every item, Nero, for example, here we have a code of 2 numbers. And so user 1 and movie Nero, if you take their code 1, 0 multiplied by 1, 0 in a vector matrix formulation, it will come down to a particular value, which is 1. And therefore, then we say, okay, 1 means that the user likes the movie. Now, the problem is that how do we find out these so-called smaller matrices? And that's essentially the matrix factorization problem. Now, of course, it may look simple, but in reality, this matrix is a lot larger, a lot bigger, is a lot more than what we see here. And the problem then becomes a bit more complex. But the key thing that characterizes the issue of recommended systems, as opposed to many other machine learning problems, essentially is the sparsity of the data. Now, think of the earlier formulation when we talk about the ratings. They come up in terms of matrix. Now, it's not possible that every user has watched all the movies. I mean, if we give you the catalog of all the movies that, let's say, Netflix has, how many have you watched? Probably it's a very small number. And therefore, if you think about that problem, it means that within this matrix that we are trying to construct of the users and the items and so on, a lot of the values are not seen, are not observed. Because simply, maybe out of the 10,000 movies, let's say, that the catalog has, well, yeah, maybe I have watched 100. But what is 100 out of 10,000? 100 out of 10,000 is only 1%. And that's a very small number. So therefore, the problem is characterized by this issue of sparsity, where maybe within the matrix, we only observe 1% to 5% of the entries. But what we are trying to do is to predict the remaining 95% or 99% of the entries. Now, that is a very difficult problem, because if you compare that to a lot of, let's say, if you're familiar with machine learning and other problems, usually when we talk about classification and so on, you probably have a training testing split of 80-20, but in the case that you train with 80% of the data you learn from, you test it on the 20%. Here is the reverse. You train on the smaller slice, but you're trying to predict the much larger slice that we don't know. And therefore, recommender system is still an ongoing problem. This is something that is still very actively being researched. So now to characterize this, this is an illustration of what we call power law. What it simply means is that if I were to rank, let's say, all the items, all the movies by popularity, then a few movies at the top is going to have very high popularity, and that kind of makes sense, right? I mean, think of every week there are probably new movies in the cinema, but everybody probably watches only one or two of those. I mean, so they are very, very popular. Now, the recommendation problem is not targeted at those. The recommendation problem is really targeted at the long tail. The long tail is the large number of items, or in this particular domain, let's say movies, where you would need to surface them to the correct users. If you show them to the wrong users, they are not going to be interested at all. But if you show them to the right users, then they're going to be interested. And therefore, that is where this recommendation problem really lies. Now, so that was kind of the basic picture of how we built the recommendations. And now we want to motivate how the modern recommender systems have started to go beyond just looking at the matrices. Because in some sense, yes, the matrices are useful, but it was 2006, that was like 17 years ago. Can we do better than that? And it turns out that we can, and the reason why we can do better than that is that along the way, there is a progression in the technology where everybody is essentially migrating to the digital media, meaning that we do a lot of things now, and we express a lot of things in very rich multimedia form. So meaning that 20 years ago, people on Netflix are probably like mailing DVDs and so on. But today we all have handphones and smartphones, and you go to Instagram, and when you go to Instagram, you basically post pictures, and I can actually get a sense of the kind of preference profiles that you might have based on the kind of visual imagery that you associate yourself with. And in a way, I think even when you're doing things online, buying products, in addition to those ratings, there are going to be a lot of information that are useful. At the same time, we can see the images. So in that sense, now I can look at the images and see what kind of images you probably prefer or don't prefer, what kind of colors you might like, what kind of brands. So all these things bring together what we call multimodality. And the modality here simply means that we can actually learn from multiple information about the user's preferences. The ratings are just one of them. We can look at the images, we can look at the textual descriptions, we can take a look at what the related products are. So in this particular example, on Amazon, you can see the picture, you can see the text, you can see what other customers who view this item also viewed. And therefore, there is a lot of information that can power the association between these different products. Now, then the modern day recommendation essentially is a combination of two things. One is the basic idea of collaborative filtering, and coming back to collaborative filtering, that essentially is learning through the behaviors. This is what we talk about when we talk about the matrices earlier. Now, at the same time, we're going to learn from the content. The content-based filtering means that I'm going to recommend to you things that are similar in content according to, based on the things that you liked before. So if you read a certain kind of books, let's say Harry Potter books, let's say, then maybe in the future I'm going to recommend to you not just other Harry Potter books, but also books about fantasy, magic, and so on, maybe because they have similar content. If you if you had watched like movies like about Star Wars or science fiction stuff, maybe in the future I'm going to recommend to you other movies that are similar along the lines of that science fiction. It could be, for example, Guardians of the Galaxy or things like that. Now, so that sort of content-based filtering is very rich in the sense that they are not just in terms of similar content, in terms of like we think about genre of books and so on, but also in terms of we can analyze for the imagery, the images, like for example, similar clothes, and the similarity itself might even be different for different users in the sense that what I consider similar could be because I'm into the brand, or what you consider similar could be because you are into the color. And therefore, we can then infuse the preferences onto these spaces of the content that can then help us to build better and better recommendation about the user. And we start to pay attention to context because it turns out that to recommend something, we actually are not just influenced by our preferences alone, but also in the very specific context in which we are undertaking those things. So for example, if you're picking a movie, it probably depends on who you're watching the movie with. If you're going with children, then of course, then you're going to be probably picking the kids' movies. If you're going with your buddies, or whether you're going with your boyfriend, girlfriend, and so on, I mean, you're probably going to be picking different movies. And therefore, essentially, the context influences the way that we are going to make these different adoption and purchases as well. And that's also a factor in modern day recommended systems as well. Now, increasingly, and this is something that is of current interest, is the question of whether can we explain these recommendations? Because it turns out that a lot of these models are data-driven, but they are data-driven in a way that they might have been derived from a complex model. And because of that, we may not always understand what's going on inside the model. And therefore, it would just spit out the recommendations. But it turns out that for human, receiving recommendation with an explanation is a lot more powerful, because then it can point to us as to some of the reasons why we might like these things. It helps us to verbalize our own preferences in a way that we ourselves may find it difficult to do. But in that sense, I think this is becoming an important area as well. Now, when we come to explanation, it turns out that, again, there are as many varied explanations as there are the kind of recommendations that you're expecting. And now I'm just going to go through a few examples to kind of just get you a sense of what are some of these different explanations that might come up. Now, the simplest kind of explanation is the one that relies on similarities. It's either similar movies or similar people. And I think here the idea is that can we recommend something and we explain it to you by, let's say, oh, this is similar to what you have watched before. Or we can say, hey, I look at your friends and a number of your friends like these movies. And therefore, you're probably going to like this movie as well. And that kind of explanation rely on the notion of neighborliness, either among the items we are trying to recommend or among the users that are going to be receiving the recommendation. Now, in some sense, this probably will work well in certain contexts, like the cultural products, like media products, because a lot of these things, sometimes we watch movies because we want to be part of the same cultural milieu as everybody else. Like we can talk about things, when we meet our friends because we watch the same things. Some of the things might be a bit more objective in the sense that, hey, maybe to you, buying something needs to be motivated by whether it meets your needs. And therefore, there are going to be certain cases where we would need to provide explanations that are in some sense more relevant to various attributes. This is probably more suitable for, let's say, consumer electronics, for example, because you buy the TV a lot of us might pay attention to different things. Some of us may want the biggest TV. Some of us pay attention to the sound quality, picture quality, or some of us want cost to be the primary motivation or brand. There are a lot of these different attributes, and then we can also derive this recommendation and explain it based on what kind of specifications that you might like. In some of the cases, there are trade-offs. Trade-offs meaning that we all want the best things, but it doesn't come cheap, for example. Or I'm trying to book a hotel, let's say for travel. I want a good location, but the one with a good location doesn't have a good service, for example, things like that. So in that case, where we are dealing with this sort of products or items to recommend that may actually have this kind of trade-off, then that's where a particular radar chart, like this is one example that we are showing here, is going to give us a sense of the trade-off between different attributes. You could see whether there are items that are, let's say, good overall in the sense that it hits most of the spots across different attributes, or you could see, well, there is an item that is supremely good in one dimension, but it's not so great in all the other ones, or you might still like that if that one dimension that is good at is exactly the thing that you're into. So I mean, sort of things like that. So and therefore, this sort of explanation helps us to manage the trade-offs of the recommendations, and therefore then might be a good way to explain things as well. We also see template-based pretty commonly, because in this case, we kind of want to know which features are performing well, which features are not performing well. We say template because they might sound repetitive, like you might be interested in this because this product performs well in that. But in a way, because they are predictable, it's also easy to kind of read them and get a sense of what it does. And increasingly, especially now with the talk of generative models and so on, we can generate the language, natural language explanation, especially if you're thinking, hey, I'm going to recommend you this book, and then we're going to provide a text that accompany that book. And this is something that is increasingly of interest as well, because in some sense, we want to be able to, especially with someone who is reading stuff like books and so on, then the kind of explanation probably that is most convincing is to tell the person in what way the book is going to be something that is interested to him or to her. So in that case, then we might want to do something like this as well. Now, for fashion, then the motivation is different. A lot of it is based on appearances, and therefore there is a lot of emphasis in terms of finding out certain explanations that could highlight different parts of an item that are particularly unique. So for example, in this case, let's say on the left side, and in terms of after recommendation, it might highlight certain areas of the images that is considered to be, hey, it looks different from the other kind of clothing. On the right side, when we start to look at product images, and we can try to find out the correspondence between what the image is showing, as well as what the text is showing in terms of the reviews, that can serve as a good explanation. So in that case, let's say the purple clothing has a nice wide neck opening. Okay, if we didn't see that, maybe we didn't kind of notice, hey, there is an interesting part of it, and there is a nice pocket size, and therefore then this sort of a explanation, especially when we shop online, where we can't touch and we can't see the things, we have to rely a lot in terms of the content that is showed to us in terms on the phone or in the computer. Now, these sort of things might actually then be useful. All right, now, what are some of the future trends? And I'm just going to talk about a couple of them, which I think are kind of useful. And after that, I'm going to tell you a bit more about where you can find some resources to look out more if you're interested in diving deeper into recommendations. Now, in the case of some of the future trends, one of them, of course, is that everybody has sort of ChatGPT. So ChatGPT is becoming very, very popular. And there is increasing interest in terms of whether there is an ability to leverage on some of the language models in order to help in the recommendation. This is still in very early stages, and I think there is a lot of attention that's being paid to how to do this. It's not always very suitable to every possible recommendation scenario, but for certain things like cultural products like books and movies, these are probably something that the language models have some understanding of, because they would have consumed content from the web. Now, this is just an example. This is an example that was actually brought up by one of my colleagues about using chat models to do the recommendation. So, for example, in this case, on the left is the prompt. So let's say someone likes Steve Jobs' biography, and let's say the recommendation list is like a few books like Who is Bill Gates, Inside Apple, Tim Cook, Business, Data Point. Can we explain to her in a very concise way whether the list makes sense? And then the chatbot is going to say, hey, the recommendation list includes books that are closely related to the topic of technology, business, leadership. It could provide additional insight and perspectives on the life and the work of Steve Jobs. So the concise summary is that the list complements a Steve Jobs biography by giving more information about Apple's corporate culture and strategy, and sheds more light on the history and evolution of personal computing in general. So I think there is going to be some usefulness to these language models in terms of even trying to explain some of the recommendations. And the recommendations here might have been generated by some black box model, but the language model now have the capacity to try to understand what those things could be and try to explain it. Now, it's still a big question mark as to whether it is going to be suitable for all sorts of models, especially for those types of product domains where the language models may not have a good coverage of. I don't know about, let's say, toys and so on. I mean, that probably needs a bit more understanding about what kind of toys it is from what it does. That's something that is that's something that we can take a look further on. Now, another future trend that I think is also increasingly interesting is actually applying federated learning. And I think in this sense, I think we point out the key problem recommendation so far is that all of us, we split our purchases across multiple shops. I might buy my books on Amazon, but I might watch my movies on Netflix, and I might buy my groceries on Redmart. So essentially, no single system is going to know everything about all the different kind of things that I do. Now, that might be a good thing from the privacy data protection point of view, but at the same time, that might also mean that each of them will build something that is inherently limited in the sense that we don't have access to a lot of users. And therefore, then federated learning deals with a system that tries to build a model that is shared across multiple sources, multiple merchants, and so on. But at the same time, they are not going to share their data directly, but instead what they're going to do is they're going to share the model. So there are going to be algorithms that allow the learning of such scenarios without breaching the data privacy and protection concerns. And the key benefit then will be the emergence of a more unified model, like a more intelligent model that can understand things beyond multiple sources. All right, so I'm going to start taking on questions very soon. But before that, I'm just going to kind of tell you a bit more about some of the things that you might be wondering. Let's say if you want to get started, how do you get started? Now, just like a lot of other AI technologies, there are now increasingly libraries that are built to support recommendation technologies. And one of them actually came from our lab that is called Cornac. It's based on Python. It's built by the Preferred AI group, and it's openly available. So you can actually just go to the website cornac.preferred.ai, and then you're going to be able to play around with it. And some of the advantages to the models is that it has a lot of inbuilt models, meaning that you don't actually need to implement a lot of the algorithms that are in the research papers and so on. But instead, you can just leverage on the things that have been built in Cornac. And in this case, Cornac also supports not just the ratings, but also in terms of when we talk about multimodality, whether it's text, images, and graph. These are different kind of modalities. And it supports experiments. Experiments meaning that a lot of times when you try an AI model, you need to compare across multiple different models and see which one actually serve your purpose well. And therefore, it supports multimodality, scalability. It is based on Python because that's pretty much the language of data science today. A lot of data scientists are probably reliant on Python, and they may want to couple this with a lot of the other models that they're building as well. But in order to make the learning more scalable, we leverage Cython. Cython is basically to make C++ code work better in terms of within a Python framework. And it makes it so easy to do experiments, essentially a data loading, evaluation method, models, metric experiments. It looks like 5 boxes, but in reality, if you were to use Cornac, this actually translates to 5 lines of code. So you write 1 line to load the data, you write 1 line to specify what kind of evaluation method you might want to do. You write another line to specify which models you want to use, another line to specify the metrics, and then you run the experiments, and it's going to produce a table of content. A table of results that that you can analyze for this. Now, a lot of these are going to be hands-on. You can watch tutorial videos. In fact, this is one of the most recent tutorials that we just did in last month in a conference. If you're interested, just go ahead to the link, and then you can watch even the video of the recordings. So that kind of gets you a sense of some of these technologies as well. The online notebooks, this is also coming from our group. In fact, I think if you follow these notebooks 1 to 9, they are pretty much have covered a lot of different aspects of recommender systems, and I think something that but this probably requires you to have a bit more foundation in terms of Python programming and maybe some machine learning as well. And finally, I think if you are into these things, right, and you kind of want to equip yourself with skills in terms that prepares you in terms of AI, the SMU has a program in Master of IT in Business, and particularly the artificial intelligence track is going to groom the next generation AI talents. And there are a lot of interesting courses that are in there, including one on recommender systems. So that's the one on the right here, right, recommender systems. And just to get you a sense of what we cover in such a course, I just exported here. This is an outline of, it's a 10-week course. Let's say what happens is that we cover multiple things, like from the introduction, some of the things that we talked about earlier, like what is matrix factorization, for example, and how do we learn them. So we look at how to do the learning so that we can do the factorization effectively. How do we evaluate recommender systems? How do we factor in multiple modalities, and how do we make use of deep learning? So deep learning goes beyond matrix factorization into neural network models to enable even recommendations with even more data sets. And some issues about contextual awareness, explanations, and yeah, coupled with some other projects. So there's a lot of hands-on component within this as well. So you learn not just in terms of the theory of it, but importantly, you get to apply them as well. All right, okay, so thanks for your patience. I think right now we're going to get a little bit to the Q&A. And I think there are a lot of, there are a couple of questions here. I think I can pick up one. First of all, from Reagan. Now, what is the most popular or preferred programming language used in developing recommender systems? Does ChatGPT have a future on this technological advancement? All right, okay, so currently the most popular language, I would say, is either Java or Python. And I think a lot of it really depends on the backend, because recommendations generally happen within the backend models. In some sense, Python is very good for prototyping, and that's why we built our recommendation library on Python. And in that case, but I have seen some Java systems as well, particularly when we see backends that are already built on Java. So really, I mean, it's not that important exactly what the language is, because the underlying model is the one that drives the recommendation. But I would say that if you're thinking about what is the most popular or preferred one, I would probably go with Python. Now, does ChatGPT have a future in technological advancement? I think we covered some of this example earlier, although very briefly. I think ChatGPT has some background knowledge that is built into it through its reading of the web content. Now, I think it depends on how much information it has about the different products and so on. Now, the difficulty that ChatGPT probably still has is that it can't really personalize it deeply, because in some sense, it doesn't yet quite have an understanding of each of us personally. And so therefore, in order to create recommendations, we need to provide ChatGPT with a lot of information in the prompt about what kind of user the person is. And that itself, that means we are limited by the expressiveness of the prompt itself, as opposed to existing neural network models that probably can learn a lot more information from implicitly from our behavior. So, but on the other hand, I think there is still some promising possibilities with ChatGPT. Especially, we see it in terms of trying to verbalize or explain these things, and that might actually be a good way where ChatGPT might power the chatbots that sits on top of recommendation models to try to explain the recommendations to the end users. That is probably something that we see going forward. Okay, so there's another question from Kibun. Well, there will be competition between different e-commerce platforms, and when we have federated models sharing different platforms, will it impact their business competitiveness? Yes, I think there is room to think that it might be, but I think in some sense, you can almost kind of imagine that if you, I mean, we could possibly refuse to cooperate with anybody else, for example, and in that way, then some of the weaker players might then gang up together and build a federated model in order for them to be able to compete with some of the bigger ones. So I think the nature of the competition, I think, is such that if you are big enough to have a good model on your own, and might be platforms such as some of the biggest ones in the world, like Amazon, Taobao, they may not need to build a federated model, at least within themselves, because they may have a lot of data already. But a lot of the smaller players in the ecosystem might be motivated, because otherwise they would not be able to compete. And therefore, now I think we see it as federation allows a channel for some of the smaller players to essentially build a consortium in order to better compete with the bigger players. In some sense, in this case, it would actually improve their competitiveness instead of weakening it. Now, on the other hand, I think we have to see the progression. I mean, this federation is basically just a piece of technology. In a way, whether the players take up the technology, I think depends also in terms of the market situations. But we generally think that if you think about the large language models like ChatGPT and things like that, they also build, they give, in some sense, an advantage to the players who make use of them. But then they can do so in a broad-based manner, and therefore it's going to help improve the whole ecosystem overall instead of just one player over another. But yeah, that's a good question. I think that is something that has to be explored in terms of its economics as well as in terms of its technology. Okay, so another question is on the ethical issues concerning recommendations. Whether Netflix, for example, Netflix recommending similar shows that might reinforce stereotypes. It is a concern in the sense that, I mean, if you, not necessarily Netflix sense, I think it's probably more in terms of like the news, as well as the Twitter, and sort of like where it shapes your worldview. So in some sense, in the system might try to recommend things to you that they think you will be reading, that you would like to read and so on. But in the process, they are not introducing you to new information. They're basically getting you into a rabbit hole of more and more information. And I think that is a concern. I think there is a branch of recommendation that takes a look at the issue of ethics. In terms of, and part of it is in terms of improving the interpretability of models. And maybe in that way, people can actually begin to see whether the recommendations, are they powered by special interests, or are they really just reacting to the user preferences, or are we actually getting things that are objective in nature? I think this is still a very evolving kind of a problem. I think it's not something that is unique to the technology recommendation. I think it's anything that is something to do with information access is going to be affected by this particular issue. Okay, another question is on the cost of setting up recommended systems. Is it costly? Is it recommended? Or even for small companies that have limited resources? The general answer, yes, it is recommended. Okay, so it's not costly. The only cost is data. Now that actually is the biggest question, whether there is enough data on the part of the SMEs to actually run these things. I think it is worth looking into. At least, some SMEs might already be sitting on top of a lot of data they haven't been using. So this might give them a channel to make use of this opportunity to build a recommendation. On the other hand, the more data you have, the better the recommended systems that you're going to build, and therefore there might be opportunities for SMEs to kind of congregate together, maybe in a consortium of sorts, to try to see whether they want to build a federation that helps them. Okay, now the next question is from Shirley. I think, is there any value in a company developing their own unique AI, or will the pace of improvement due to open sources and get any advantages quickly? Okay, so there isn't our own AI per se in that sense. I think here the context is just whether are we able to, because the AIs that everybody built is going to be based on more or less similar types of technology. Now it comes down to whether they have a comparative advantage. And usually the comparative advantage lies in terms of either they are better executing the AI for the specific business cases, or they have some access to the data that to some unique data that nobody else has. Now, in some sense, most companies probably are going to build on top of existing resources, because the current AI leverages on a lot of data. Now, on the other hand, there's going to be some pieces of the AI technology that are going to be more sensitive, that you may not be able to give it up to some other players. I mean, in some sense, if you talk about language models like ChatGPT and so on, it's basically learning how to deal with natural languages and so on. This is a capacity that is not unique to a particular company. It's a capacity that most companies need, and no company needs to build it on its own, because it's really about understanding of language. But I think if we talk about some degree of data-driven technologies that involve sensitive customer data, as recommended systems is, I think then there is probably value in trying to leverage on that within the company, because what other choices do we have in terms of, otherwise do we just export the customer data to somewhere else, and that might actually run counter against all these data privacy protection issues. And therefore, some of this data might actually have to be done in-house. And I think recommended systems probably is one of those things where there is a lot of benefit to looking into leveraging on our own data to build something that actually at least serves our own customers well. All right, thank you for the many questions that everybody has done. I think with this, I think I'm going to wrap up this.